now we have a two-part talk, dispersion in a fixed dimension. And the first part is by Boris Bukh. So please, you have 1 hour.
Well, it's 45 minutes according to the schedule. Thank you, Igor. Hello, everyone. Thank you for coming. Again, I can see every one of you. I have enough monitors. So it's a Blackboard talk. So please don't hesitate to stop me, ask questions or anything. So, okay. So I will be talking about this mostly dispersion, but I will be also talking about something discrepancy related in a talk. So as Igor mentioned, it's a two-part talk. The first part, I will give a general introduction. I will talk about lower bounds, and then Tingwei in the second part will talk about constructions. So, which is actually harder part. So this is the fair division of labor. Okay. So I'll be talking about the fixed dimension. So basically, quantitatively we heard about dispersion, it will be in a fixed dimension. So let me just introduce my own notation. I will not repeat the definition. I just want to introduce the notation. So I will denote by MD of n to be the optimal dispersion of n points in dimension n and unit cube. So formally speaking, this is the minimum dispersion of n point set in 0, 1 to the d. Okay, so with this again, as in other talks, with respect to the axis parallel boxes. So as it was mentioned again in several talks, including the last one by Sasha, this quantity behaves like some constant over n. So, okay, let me just first of all tell you to start a trivial lower bound. So trivial lower bound is 1 over n plus 1. So let me just do a proof by picture. Okay, so my pictures will be in dimension 2, simply because my board is two-dimensional, but we haven't upgraded it yet. But what I'll be saying will be in a general dimension. So this bound is okay. What does it say? It means if I take any set of n points, I can find an empty axis parallel box of this volume. Well, it's rather simple. What you do, you take these n points, you project them down on one of the coordinate axes. I'll project down onto the x coordinate. So this is my projections. So I get points on the x coordinate axis. These are my points. By the way, can people see it well? Is it in focus? Can Santana tell you how readable is this?
It's okay. I can see it.
Okay, excellent. Again, and if things go wrong, I can adjust both the settings on the camera. Also, I can change the settings on the zoom to trade the bandwidth for quality, for frame rate for quality, etc. So please let me know. Thank you.
Okay.
Okay. So because now you have a bunch of points on the interval from 0 to 1, and usually the n points, they divide the interval into n plus 1 intervals. So about this one of these intervals will have area this much. So say in this picture, I think it's going to be this interval, which looks the biggest to me. And then just take this big box, just take pre-image of this interval in my cube. And this will have volume 1 over n plus 1. Easy. Upper bounds are harder. And as again, all the talks were really about constructions and upper bounds. So the general spirit of this construction, there is some kind of constant, depends on the construction, depends on things, which achieves same growth. So dependency on n is correct. It's a constant over n. And okay, what we'll be talking about in this talk is this constant. What's the best value of this constant you can make? Okay. So as far as I am aware, well, there are the first kind of construction which gets us any kind of finite bound on this. It was by Hilton Hammersley, and again, and many of the constructions, not all, but many of the constructions are are similar flavor to Hilton Hammersley construction. And Tingway in his part of the talk will talk more about it. What I want to mention now is that I can look. I want to look at the optimal constant, and so I will define quantity which is denoted by little c of d to be it's the limit as n goes to infinity of n times this optimal dispersion. Okay. I need to, again, it's not difficult to show that the limit actually exists. Okay, I will not go through the proof. It's not long, but the basic idea is, okay, if I have some point set of say 2 endpoints, say, I can cut it in half, endpoints left, endpoints on the right, and then use whatever way I know of finding a large empty box among endpoints to find the large empty box among these 2 endpoints. Okay, and of course, number 2 is arbitrary. You could cut it into any number of pieces. And that it gives you some kind of monotonicity argument, and monotone sequences converge. Okay, something, again, not difficult. Argument of that spirit shows that limit exists. So what do we know about this constant? Again, so for me, d will be fixed. And again, I'm interested in this quantity. Unlike, for example, what Sasha was talking about, both d and n were growing. He had talked about various regimes, which is not what this talk is about. So the best construction prior to our work was due to Larcher, which is based on the nets construction by singular the writer, which is a sort of modification of the Hilton Hammersley, but with again with some additional ideas, which again I will not get into, which gave us a bound which is again exponential indeed. This is all I want you to see from this. It's an exponential function of d. And the best lower bound, again, was an improvement on this, was logarithmic indeed. So it was quarter log d. And again, let me make sure I don't misspell anybody's names. So Eisleitner, Hinrich, and Rudolph. Okay. For the lower bound. So what we managed to do, we managed to show that this quantity C of d grows polynomially with d. So so what we can prove, okay. So lower bound is linear in d. Again, constant is 2 over e in large dimensions. Again, this you can improve a little bit, but again, I'm not going to spend time on some minor improvements. And the upper bound is some constant. I think in the paper it was 8,000, but it's just okay. Whatever was we wrote down, it could be optimized for. That's not important. but upper bound is d squared log. All right. So I will tell you a bit later, about this construction. Sorry, about this lower bound, and we also like much of this subject, we were also interested in looking not only at the all the axis parallel boxes, but also at the boxes which are what would be called basic boxes, for example, dyadic boxes. So, for example, like these constructions, for Hilton-Hammersley, a lot modifications such as those of Larcher, and much of the literature concerns about those kind of TMS net constructions and similar things. So we also have a version of these results for those. So let me just mention that. So for that, let me define what are those basic boxes. Basic box is a box that is a product of basic intervals. Again, in some base Q. So what are those? So basic interval, it's an interval. You should think of dyadic intervals. So except I'm going to, in general, there's going to be some base Q. So Q to the M, A plus 1, Q to the M. Okay, and so I'm looking at the boxes that are products of such okay. Again, the reason people look at the basic boxes is because sometimes one can, by proving results about basic boxes, you can then derive results about arbitrary boxes by some kind of argument. For example, one contains the other, or and also oftentimes they're actually sufficient for various applications. So so as was discussed in the Vladimir's talk, what we want, for example, in discrepancy problem, we want the number of points in the box to be what you expect. So we define, and it's and for us, and M epsilon. Sorry. Oops. Let me just get it right, because I will. M epsilon L must net. To be set P 1 for n D. Let me just make sure. Of size Q to the n times M. Such that this set has the expected number of points in any box of the volume Q to the negative n, such that every basic box of volume q to the negative n has between 1 minus epsilon m and 1 over plus epsilon m. Okay. So on average, a box of this volume will have m points. Okay. And okay, we cannot, as we will see later in the talk, we cannot expect that every box of this volume will have exactly m points. That would be what's called a net. And if you want to have we cannot expect this to happen if for small boxes. But if you're allowing yourself a little bit of slack, just an epsilon, then we're getting a weakening of what we normally call the net. So net would be normally where epsilon is 0, and which we will call an Elmas net. Okay. So again, I'm sure many of you know about nets in this audience. But our notation is slightly different because we want to emphasize slightly different aspect of it. So what is known about constructing such bits? Well, if you want to construct epsilon equals 0, then this one is called nets, and we need to take m to be exponential in the dimension. So, in other words, you cannot assure that like very, very small boxes have right number of points. Exactly right. And for more it's sharp. And this is sharp. And I will not again. Again, we don't know what the best value of this constancy is, but we know that both the lower bound and upper bound are this constant. So what we can construct using the similar ideas to Gaussian construction for this sets of flow dispersion. For every fixed epsilon, for every fixed positive epsilon, a set and m epsilon Elmas net of polynomial size. So polynomial indeed, not exponential. So of size, again, big O of d log d. All right. There was a question. Okay.
No.
No, because I heard some sound. All right. Any questions about the results? All right. So plan for my part of the talk is I will tell you the lower bound for the dispersion, which is new. I will tell you a bit about the lower bound, about this m epsilon and Elmas nets, which also actually gives you, we believe, a new way of proving this lower bound, where an epsilon is 0. And then after meeting, we will tell you about constructions. So let's do proofs. So lower bound on CD, which is, to remind you, it's the limit of the n times MD n goes to infinity. So this is dispersion of a endpoint set in the dimension. So I will start with proving a weaker lower bound than I told you. So remember, I told you that we proved a linear lower bound. I will tell you first a proof of a lower bound which is a logarithm factor worse, but it will be easier to see what the idea is from that proof, and then I will tell you what do you need to alter to make the actual bound, to obtain the bound we actually claim. Okay, so proof of the bound that CD is at least d over log d times sort of constant. Times some constant C couplet. So I'm going to look at boxes of volume R over N. So I'm going to choose some number R0, which will be chosen later. And I'm going to look at the box of volume B R0 over N. And I'll make this box centered at the origin. So my B is going to be a box from minus delta to plus delta in a D. So my picture, I mean, I'll draw a lot of boxes today. So this is my 0, 1 to the D, again, in the plane. And I want to look at where it translates of this box. So I will be looking at things like this. So this is my B plus X. So where X is this point. Is this too small for people to read, this X?
I think no, we couldn't see it, but you say that this is X.
Okay, I'm glad that you trust me. It's okay. So I will draw bigger then. Okay, that's good. Okay, I see.
Yeah.
Nodding. Okay. So I'm going to look at a translate of this. Okay, this is really a small box, but again, due to the medium, it looks big. So what I'm going to look at also a small box inside this, well, even smaller box inside this small box. So I'm also going to look at the B0, which is inside B, whose volume is going to be 1/2. So I'm going to also look at this, at a small box. So B0 will have a volume of 1/2 over N. So R0 will be large. It will go to infinity, where this is actually fairly small. So and in a box of this size, I expect to see about R0 points on average. In a box of this size, on average, I'm expecting to see 1/2 point. So it means half the time there won't be anything there. So this is a small box inside this box. All right. And again, also centered at the origin. So center at the origin. So, okay. Okay, so now I'm going to pick a random placement of this box. So I'm also picking X at random. I'm just looking what will happen. So I'm going to pick X at random. Well, when I do that, these boxes, well, both of those boxes, the small box and the big box, they will intersect some points of my point set. So remember I have some points at P. P has n points. And my goal is to find a large empty box which not contains any points of P. Of course, I mean, again, if I pick some box like this large and I place it somewhere randomly, of course, I mean, very likely I will contain some points of P because R is large, R not as large. So let me draw a picture. So again, I will draw a picture slightly fake because I mean, I'm only in 2 dimensions and this is all about D going to infinity. So I will only draw I only will draw 2. Okay, let me just try to make it big. Okay, hopefully this is big enough. So I will draw the 1 point here, and I will draw maybe another point over here. Okay, so I intercepted the point P, set P, in 2 points in this picture. So what I'm going to do now, I'm going to now cut off some parts of my box, this box B plus X, so in a way so that the new box contains no points of P. Now, I will only do that if no point is actually hits the central box, the small box, because it's very difficult to cut this box and still have much left if I hit the center. Like hitting the center is really bad for me. But the good news, the center is very small, so it's not likely to happen. Okay, so let's write that. So I can imagine just for simplicity. So let me look at just translate this whole picture. So everything is now, this is the origin. So I'm looking now at the points at P minus X. So now I'm now thinking, just draw a picture bigger, same picture, but it's blown up. This is my origin. Now, and there's a point of P here, point of P here. And for each point of this set, I want to cut something off. So what I'll do, I will cut off here. So like the scissors. I remove all of this part here. So this way, this new box will not contain this point. And similarly, I will do this here. I will cut it off. So what I'll be left, I will be left with this box. Okay, this is the idea. Okay, so for each point of this set, okay, I need to decide which coordinate I'm going to cut off, right? Well, okay, well, so imagine, for example, my had a point here. Like, should I cut an X coordinate or Y coordinate? Which coordinate should I cut for this if I want to get rid of this point?
The X one.
Yeah, of course, X. I mean, if I cut Y, I mean, I kill half of my set. Igor is right. I should cut like this. So for each point P, I'm going to choose the coordinate. Choose coordinate among 1 through Z, such that the P is largest in that coordinate, so that the Pi is the maximum of all the coordinates of the system. Right. That's how I'm choosing them. I'm going to choose farthermost one. Okay, good. Camera went out, I know. I'll fix it. Okay. You should be able to see it again.
Yeah.
Okay, so in this sketch, in this kind of easier proof, what I'll do, I will be even slightly wasteful. When I cut things off to make my calculation slightly easier, I will not cut off just only one flower. So it was only this, but at this point, I cut this part off. But what I want to do, I want to also cut symmetrically on the other side as well. Okay, so this is wasteful, but it will make my calculations easier. So let me do that, and it's going to affect result by like factor of 2 or so. So it's not going to matter much. Okay, so what I'm losing, so I lose a factor of, well, okay, well, this thing, of course, is known as the L infinity norm of this point, right? It is the largest coordinate. So what I'm losing, well, before this distance was delta, right, from the origin, it's the minus delta to delta box. And now this became this L infinity norm of this point P. So now, so what I lost is I lost a factor of L infinity norm of P divided by delta. That's what I lost. Good. Okay, so now let's finish the simpler proof. So what's the probability we're going to hit the center? Because if we're hitting the center, this is a huge loss, and this is going to be disaster. So let's not do that. So probability, this P minus X intersects the small box of the volume 1/2. Well, it's going to be at most a half or so, right? Because on average, the small box contains half a point, and therefore at least half the time it should be empty. Oh, sorry, probability this is non-empty. So it's at most a half. So, and now again, we don't want to cut off too much. We do not want to have too many points. So we expect the number of points which hits the big box to be approximately R0. Again, I say it's not exactly equal because of the boundary effects, right? Because if it were a torus, it would be exactly equal. But if I just really average over all ways to place this small box in this big 0, 1 box, the boundary count is counted a little bit less than the center. So, okay, small calculations, it's easy, but it's extremely close to R0. Okay, it's approximately R0. In particular, the probability that it's too large. So that we're going to get, I mean, I don't know, more than 3 times 20 points. Well, it's at most a third. Again, approximately, because if the on averages are not, it's not likely to be 3 times larger. So therefore, there is a way to choose the center so that we neither hit the center of the box, this tiny box inside, nor we have too many points total. So let's do that. All right. So I'm going to choose X such that the B plus X P contains fewer than 3 R0 points, and B naught plus X is empty. And I can do it. And I go to then I do this. So what did we lose? So what's the cut off decides, as explained, what's the volume of the remaining box. We obtain a box of volume. Well, first of all, it started off as being a volume R0 over n, and then we lost a bunch of times. Okay, each time we lose, we are losing this factor, but none of the points are in the center. So the L infinity norm is at least the dth root of 1/2. So okay, so each time we are losing a factor of 1 over 2 R naught to the power 1 over d. So again, so if we lost d times, if we had needed to lose d times, we would go from a box of size R naught to the box of size 1/2. So if we had d points to worry about, we would end up with just the central box. And so we take this and we raise it to however many points we contain. So and remember, we contain at most 3 R naught points. So this is a pessimistic bound, because in which we lose this much, at most that many times. Okay, so now this question is just pick a value of R naught, optimize, and be done. So let's just do it to see what our numbers come out. Okay, I think this picture we already know. This picture we already have. So let me keep this picture on the board and do the calculations of it. Okay, so this is, well, 1 over n R naught times and the exponential of 1 over d times the log 1 over 2 R naught times, well, 3 R naught. Okay, so now I'm going to choose my R naught to be d over log d. Okay, so what happens here? This is going to be d over log d. This d will cancel this d, so we'll get a 1 over log, and this is logarithmic in d. So what we're going to get 1 over n R naught times some constant, because this thing will just become a constant. Okay, and that's it. Okay, we can compute what this constant is, and I haven't tried to optimize this constant, but you see that you're getting d over log d bound times some constant. Okay, so let's now optimize it. Okay, and the main loss which we suffered, where did we lose this log, is by looking only at being very pessimistic. So for each point, we said, well, it may be very close to the center, and so we're going to lose this factor. But let's be not as pessimistic. So on a naive level, what we're doing next, we take our box, instead of considering the center and everything else, we're considering maybe 3 such levels. Like we are very in the center, we don't want to get old. We are close to the center, but not in the center, which is bad. But if there's maybe 1 or 2 points, it's kind of okay. And we are far from the center. Well, we can afford lots of points there. Okay, so we can do this kind of instead of just 2 kind of sets, maybe 3 or even more. Or of course, in limit, as we have more and more of this, okay, what we're doing, we are really assigning some kind of penalty to each point. So the penalty assigned to a point depends how close it is to in L infinity norm to the center. And we want going to weigh our points according to this penalty function. And we just want to say total penalty is small. Okay, so what we're going to do, we're going to define a penalty function. So f is just going to be some function from 0 to r naught, which is just arbitrary real function which gives us some negative numbers, penalties, how much we don't like these points, which is this far from us. So 0 corresponds being in the center. The r naught corresponds to being at the boundary. And again, so formally speaking, what I'm defining is the function f of x, which is f of 2 to the d. Oh my God! Okay, I will get it wrong because it's always super annoying. It's just the appropriate function 2 to the d. Yeah. R to the d times n, where r is the L infinity norm. Okay, the meaning of this, you just look at the cube of whose side length is equal to the L infinity norm of x, and you look at what's the volume of this cube. Okay, so this is the picture you should have in mind, and this is actually a formula which makes it true. So this is my penalty, and I'm going to weigh the points with that penalty. So this is my penalty function. Again, by averaging gives you that we can find x such that the sum of the penalties is going to be at most the mass of this penalty function. Okay, so this is again, it's just a Fubini argument. Again, on average, this is these are basically equal if you just average over all possible points. So this is p over. Sorry, I should have written. All right. So if you pick a random x, this is basically equality. So therefore, there exists an x of which is going to be true. And now the only question is, well, what's the right penalty function to choose? And the penalty function, of course, should be exactly how much we lose. So we're going to choose. My penalty function is going to be f of r is the log r naught over r. And the point of this choice, you're going to get your f of x is this. Okay. Really, so so that means this is the logarithm of the loss we're suffering. So remember, loss we're suffering is delta over L infinity norm of the point. So this is literally logarithm of that. So this, if I added the penalties, it's exactly the logarithm of the loss we're suffering. Okay, now you do the calculations, just the same calculation as I showed here, and you're going to get this lower bound, which is linear in D now. And okay, it will be a factor of 2 worse because we're still doing this cutting off two sides symmetrically, even though we don't need to. And if you're being more careful, is to cut off on one side and just use appropriate inequality, you can save the factor of 2 as well. Okay, that's really all there is to the lower bound. Okay, I believe I have a couple of more minutes. Boris nodding, good. Okay. Last thing I want is basically get like wrath of the organizers, and they never invite me to talk again. So okay, and I want to tell you about these lower bounds on the nets, and the Almas nets and exact nets. again, I don't want to be as detailed of a proof as this one, but I want to give you an idea there. Any questions about this proof before I actually switch gears? Or okay. Okay, so just an idea of that, because I think, again, quite a few people here worked on the nets or thought about the nets. So recall what, so a net is a set containing expected number of points in every, let's say, okay, dyadic box. Again, so I'm doing Q equals 2 case just so that it's easier for me to say and it's easier for me to draw things. The general case is similar to just more notation. So what am I going to do? We're going to first pick some small box. Let me just make sure I will get it right. So take some box which is true to the n over 2k for some value of k. We're going to choose times 0, 1 to the 0, 1, 2k. So this is my n, and this is my, sorry, d minus 1. Right. So what it's just done, I just say, let's look at some sub box of this. So let me do the picture. So I have a box. I'm interested in the boxes of certain volume, and I'm just looking at certain sub box of that. And again, just it's enough to show that I cannot have two uniform distribution inside this sub box, like this over half. Okay, that's clearly enough. And then I will look at sub boxes of this box, and I'm going to look at the first the binary digits of points in that box. So pick a random point and pick a random point P from this box intersection. The first binary digits of P, I mean, in each of the d coordinates, in each of d coordinates is going to be random. And so, for example, okay, so like let me just say, look at the if I'm interested in the first y coordinate, so I'm looking at this box here. This is the box I'm looking. I'm picking a random point. Now the first, so what will happen is I'm looking whether I'm in this box, this box, this box, or this box, and this will determine the first digits in x, y, and y coordinates. I'm looking at all d of them. And if the number of points is about equal in each of the small boxes, these are going to be these coordinates, each of the coordinates, going to be essentially independent random variables. So what was the number of points in each of these boxes is basically the same. So I have a bunch of independent random variables, and the question is, how big can this probability space be if I have a bunch of independent random variables supporting this space? Okay, this is extremely well studied problem. Okay, well, again, I don't have time to explain the argument. It's like 10-15 minutes to explain the argument, but it's an easy argument giving tight lower bounds, like literally tight lower bounds on this problem, and that's it. And okay, you need to do the same thing for. Okay, now that we have several coordinates, that's the two digits, so the 0, 1 valid variables, 0, 1, 2, q minus 1 variables. And you're really actually working not like completely independent random variables, but k-wise independent random variables, because this actually gives you better bound. But end of the day, we're taking the radio off-the-shelf idea and just noticing that this is independent random variables and we're getting it bound. Okay, that's it for my talk. I think I have no time left. Thank you for all of you for your attention.
Yes, thank you very much. Are there any questions or comments? Questions? So, and maybe I have a question. In the last part of your talk, you spoke about the collection of independent random variables, and what is the bound? Maybe some simple
So
bound.
the bound is,
It is exponential. Am I right?
Yes, we're getting exponential bound for an epsilon is 0. Okay, so let me just copy it because again I don't. So okay, so bound is the following. So so remember m epsilon net, and epsilon net means the intersection with the box is between 1 plus epsilon m and 1 minus epsilon times m. Okay, so this is what it means. And so the bound is the following. So m is going to be at least q to the negative 2k minus 2. There's some constant here, times epsilon minus 2. If epsilon is smaller than 1 over 2 times square root the dimension and not too small. But if it's just this is just to prevent this term from blowing up. Of course, if you want to get bound for exactly for epsilon 0, you can just take epsilon to be this number and you get to the bound. Okay, so this is bound, and it gets become bound when epsilon is constant, which is I mean 1 over epsilon squared times some factors in d. Okay. It's not the best bound known. Again, the best bounds known are better than this in this regime. But I think it is probably the simplest proof there is.
Yeah, thank you. Are there any other questions or comments? So maybe if we do not have any questions, then we have a 7 minutes break, and then the second part of the talk. So let us thank Boris again.
Thank you. Thank you, Igor.
Yeah, 7 minutes break.